Good morning, class. Hope all of you are doing well. And we are on the last part of this chapter 6, which is power. So, as you must be aware, that there are two other PowerPoints that are uploaded in the last week's folder. So, this is the final part of your chapter 6. So, today we will be discussing power and what actually is the meaning of the word power. I know power is, everybody wants power, but in physics power has a different meaning, and we have electrical power, we have power inside our body to do the work. And basically power, the word conjures up many images. For example, a professional football player muscling aside his opponent has a different meaning of power, or a dragster roaring away from the starting line has another meaning of power. And for example, natural power power in nature, for example, a volcano blowing its lava into the atmosphere, or if it is a rocket blasting off. So different scenarios use power differently. And so basically the actual definition of the power is the rate at which work is done. And the average power, if you see, we have a symbol over here. We say average power because there's a line over it, so we use it as an average power, is basically given by the work that is done for a period of time. So work done over time is power. And how do you do the work? Because you're converting energy. It's the energy that has been transformed into work. So for example, if you're walking up the stairs, you will not be able to walk up the stairs if you don't have the energy to walk up. If you've not eaten for 10 days or a week, your power will be zero because you do not have the energy to do the work. So basically, there should be an intrinsic energy which will allow you to do the work. So then coming back to our usual, how do we measure and what are the units of power? So the units of power is basically based on the formula. We know that formula for power is work upon time. So work is normally measured in joules and time is measured in seconds. So we get one joule over 1 second has been named as 1 watt. You are used to seeing these units on the electrical appliances. You must have seen it on the bulb itself. 30 watt bulb, 60 watt bulb, 100 watt bulb, and different wattages for the bulbs associated. And similarly, when you eat and you do work, you are also having power, or your output is the power. So that is also measured in watts. 1 watt, 20 watt, 30 watts is basically a very small unit of power. So a 60 watt light bulb, for example, must be doing 60 joules of work per second. So that is why it became a 60 watt bulb. So great power means a large amount of work or energy developed in short period of time. For example, when a car or a powerful car accelerates rapidly, it does a large amount of work and consumes large amount of fuel in short time. So these motor racing arcades and all, they use a lot of fuel to get a lot of work done and consequently have a lot of power. So how do we calculate power? So basically, we were going to do a lab if we were physically present in the classroom, something similar to this example. You would have different groups going up and down the stairs and measuring the time and the height and checking out how much power each person had while going up and down the stairs. And you would see that different people have different power based on their mass, their speed, and the output cannot be same for everybody. So what is the for this example, let us calculate as if we are actually doing it. So what is the power output for a 60 kg woman who runs up a 3-meter high flight of stairs in 3.50 seconds, starting from rest but having a final speed of 2 meters per second. So basically, when we are standing at the bottom of the stairs, your energy is completely zero, because you have not your potential energy is zero, your kinetic energy is also zero. But when you go all the way up, your potential energy is increasing, and you're also running, so you must be having kinetic energy as well. So how do we approach this problem? So at the bottom of the stairs, we take both kinetic energy and potential energy as zero. And at the top of the stairs, we take both of them having some value. So we follow the usual conservation of energy rule, and assuming that no non-conservative forces are acting. So we will assume that change in Ke plus change in Pe must be equivalent to 0. So note down, our initial velocity is 0 because we're starting from rest. Our initial height is 0 because we are at the ground level. So the final speed is given as 2 meters per second, and the final height is given as 3 meters. And also we have to find power. So the time is given as 3.50 seconds, 3.50 seconds, and the mass of the person is given as 60.0 kg. So 3 sig figs here. So I will begin by finding the work done, because change in Ke plus change in Pe is basically the amount of work being done. So that should be equivalent to 1 by 2 mv square minus 1 by 2 mv naught square. I always like to write the entire equation and then see what is cancelling and what is not cancelling. So that's the best way to do. Minus mgh and mgh naught. That's for the potential energy, must be equivalent to 0. Since the initial potential energy is 0 and the initial kinetic energy is 0, we are left with just two terms, and work done therefore is equivalent to 1 by 2 mv square, right, and plus mgh. All you have to do is find out this work done. So the work done is only dependent on the final position and the final speed. So substituting the values, and once you substitute these values, you should get a certain number. So go ahead and work on the numbers here. That's equivalent to 1 by 2. Mass is 60.0 kgs. V squared is your 2.0 meters per second whole square, plus m, again your mass of the person, 60.0 kgs. G is the acceleration due to gravity, 9.8 meters per second square, and multiplied by h, the final position, 3.00 m. So I'll take a pause and let you find out this value. So when I solve this part, I get 120 joules, and when I solve 60 multiplied by 9.8 into 3, so I get 1764 joules. All right, and this is my work done. So you can solve and find out what is 120. Let's take a little break and add them up, since I'm doing simultaneously with you guys. So that's 4, 8, 8, and 1. So you found out that the work done is 1884 joules. Go ahead and find out the power now. power is basically work done over time taken. Okay, so 1884 joules over the time, that is 3.50 seconds. And once you solve this, the amount of power you have while going up the stairs is 538 watts. Remember, we have a new unit now, 1 watt, which is W. W is also the symbol for work done, but when we are using it as a unit of power, you know that watt stands for 1 joule over second. If you're comfortable writing watt, you can write just watt every time you're writing W. That's also fine. So the woman does 1764 joules of work to move up the stairs compared to 120 joules to increase her kinetic energy. Thus, most of our power output is required for climbing rather than accelerating. So that is where the energy output is coming from. All right. So next, let us go ahead and solve some textbook problems. And why don't you take a look at it, read the problem, and start working while I'm also working on them. So that's the best way, utilization of the time. So show that 1 British horsepower. So this is a unit conversion problem. And next, this entire problem is unit conversion. So we are going to convert from British horsepower to watts and so on and so forth. So let's see what happens here. So for part A, we have 1 horsepower. So in some countries, power is measured in horsepowers, and here we use kilowatts, megawatts. Bigger units are measured in a mega, kilo, or other units. Horsepower is a very big unit too, so a watt is a very small unit. 1 horsepower is already given equivalent to 550 feet. You know that in British they use pounds and feet system, pound per second. All right, and or maybe we'll write it for pounds per second. This is 1 horsepower in British units. In British units, 1 horsepower is 550 feet pounds per second. Our job is to convert it into watts. Okay, so 1 pound basically is 4.45 newtons is 1 pound. This is a different, it's not mass, it's the weight in British units. And our feet, we have to convert into SI units. We want the units to be all in meters, kilograms, and seconds. And similarly, 1 meter is basically 3.28 feet. 3.28 feet. Okay. Do you know why we want Newton into meter? Because work done is basically, the second part of it is work done is force into distance. Force is Newton, distance is meter, and the second from here will give us the power. So that becomes watt. Newton meter is nothing but work done. Work is measured in joules, so that is a joule per second. Okay. And therefore, when we convert 500 feet into is to be converted into meters, and a pounds is converted, pounds as a weight is converted into newtons, and second we are retaining because we need that. So we'll have 1 horsepower is going away, 1 pound is going away, and feet is going away too. So we are left with 550 multiplied by 4.45 Newton meters over seconds. The second comes from here. Rest all is going. So when you multiply this, you will get conversion of 746 Newton meter over second. Now let me remind you, Newton meter is joule, because work done, Newton meter is the unit of work. So Newton meter means 1 joule. 1 Newton into 1 meter is 1 joule. So I can safely write 1 horsepower must be equivalent to 746 joules per second. That simply means 746 watts. So you don't have to memorize this number. If I give you a problem with horsepower, I'll also give you the conversion. But as a problem, if I give you, then you will get the conversion for 1 pound. So 1 pound as weight is 4.45 Newton. You will get these conversions. And also I'll give you 1 meter is 3.28 feet. So you don't have to worry. Only thing that you have to remember is how to convert. All right. So this was its A part. The B part, I ran out of space. So let me see if I can add. Doesn't show here. For B part, let me go over here. It's not going to take too much space. So B part tells us to convert what is the horsepower rating of 75 watt light bulb. So how much is the horsepower rating for a 75 watt bulb? So that means convert 75 watts into horsepowers. So 75 watt will be equivalent to, sorry for the tight spacing, but I think we should be able to fit in this space. So for B part, you'll have 75 watts will be equivalent to 75 watts. I want horsepowers, so 1 horsepower on top and 746 watts in the denominator, because you are converting from watts to horsepower, so watt and watt is going away, and you're left with 75 divided by 746 horsepower. So obviously 75 watts will be a very small unit in horsepower. So that comes out to be 0.10 horsepower. So this is the conversion from watts to horsepower, and the A part was to convert horsepower to watts via the British power of units. All right. So let's look at another problem. Basically, there is no other new formula to be learned. We are going to simply focus on power is equivalent to work upon time, and we will not forget that work can be represented by conservation of energy sometimes. It can be also represented by work energy theorem, that is, work done is equivalent to change in kinetic energy. So you can even have it that way. So you have to understand the problem basically. So now we have this again, a textbook problem which says an 85 kg football player traveling at 5 meters per second is stopped. Do not ignore these words because it tells you something. Is stopped means its velocity must be, final velocity must be 0 in 1.0 seconds by a tackler. So there are two parts to it. What is the original kinetic energy of the player, and what average power is required to stop him? So basically you're finding out the work done in the part 1, and then you're going to find out what is the power. So let's divide it in 2 parts so that we don't run out of space again. And number 59. So we say that what is the change in kinetic energy here? So mass of the person is 85 kgs, and initial speed v naught is 5.0 meters per second, right? And The final speed is 0 meters per second, and time given is 1.0 seconds. So basically here we will say that work done, because the speed is reduced, we'll just talk about the positive value here. Work done is change in kinetic energy, that is 1 by 2 m v squared minus 1 by 2 m v naught squared is the work done. We have negative work done because of the reduced speed, so we get minus 1 by 2 m v naught squared. That is 1 by 2, whatever is the mass is 85 kgs, multiplied by v naught, which is 5.0 whole square. This work done is in joules. If I take simply the magnitude of the work done, that will be given by 1062 joules. If I use the 2 sig fig that is given throughout this problem, so we can reduce it to 1100 joules. That's my work done. In part B, you can then find the average power. So the average power is given by this magnitude of the work done over time. And we already know the work done here is 1100 joules over the time taken is 1.0 seconds. Hence the average power is 1100 watts, because the time was 1.0. So basically a very simple problem. So I hope you're getting hang of solving power related problems, and basically you're converting work done and then you're finding power is equivalent to work upon time. So next problem is a shot putter accelerates a 7.3 kg shot from rest to 14 meters per second in 1.5 seconds. What is the average power developed? Now this is a different problem from the previous one. Here the speed is increasing, so the work done is positive. So we can do it in one step if you want. The mass is given as 7.3 kgs and initial velocity is 0. Final velocity is 14 meters per second. 14 meters per second, and time given is 1.5 seconds. So remember to draw your sketches also with these problems. So a shot putter accelerates from rest up to a speed of 14 meters per second. So you can give the work done, or power is equivalent to work done over time. You don't have to do it in 2 steps. You can show it in 1 step as work done is change in kinetic energy. This is work energy theorem. And change in kinetic energy is simply 1 over 2 mv squared minus 1 over 2 mv naught squared divided by t. But since the initial velocity is 0, that term becomes 0. You're left with power is equivalent to 1 by 2 mv squared divided by t. Substitute the values and go ahead and find out. So 1 by 2 multiplied by 7.3 kgs multiplied by your 14 meters per second whole squared divided by time of 1.5 seconds. So take a little while and go ahead and solve this. You can always pause the slide here and work on the problems. Whenever I'm starting a problem, you can pause the video, read the problem slowly, solve it before I solve it for you, so that you can learn while you are reading as well. So the value comes out to be as 476 476.9 watts, but since I'm going to keep 2 sig figs, I will approximate it to 480 watts. So the average power is given by 480 watts. All right. And then the only way to learn about different scenarios is just by doing more problems. So there's one last one that I'm going to do, and I will be giving you solutions for many more. But basically in the three video lectures and 3 PowerPoints that I also upload along with the video lectures, you have lots of problems that are solved, and the class problem worksheet is also there, so you can look at the solutions from the slides. And finally, I'll also upload the solutions for them separately, but while learning you can use the slides. So I think the last problem in the scenario, a 975 kg sports car accelerates from rest to 95 kilometers per hour in 6.4 seconds. What is the average power delivered by the engine, and convert that power from watts to horsepower? So basically first you find out the power, just like you found out for all other problems, and then in the end convert the units from watt to horsepower. So the average power is the energy transferred per unit time, and the energy transformed is the change in kinetic energy of the car. So it's a typical work energy problem where the work done is basically conversion of change in KE. And the change in KE is 1/2 mv squared, that is final, minus 1/2 mv naught square, which is initial. Since in this problem we know that v naught, it's accelerating from rest, so initial velocity is 0, final velocity is 95 kilometers per hour. Again, you cannot keep it in kilometers per hour. You cannot have a unit mismatch. Everything in SI unit has to be meters per second, kgs, and so on. So 95 into 1000 meters, this is the conversion. 1 hour is 3600 seconds. I'm doing these conversions a little fast, but you know how to do the unit conversions right from chapter 2 onwards. And when you solve this, the value should come out to be 26.38 meters per second. So we can go ahead and find out the work done. The average work done is 1/2 mv squared minus 0, because my initial energy was initial work done was 0, or initial kinetic energy was 0. So that is 1/2. Mass is 975 kgs, and the final speed is 26.38 meters per second whole square. Therefore we can find the average power now. The average power will be this work 1/2. It's up to you if you want to find out the value in joules first, whatever value comes over here. I'm doing it in one step, but it's your choice how to find the values. 26.38 meters per second. I normally tell students to solve in steps. That is actually a better idea, rather than having everything in one place and messing up the calculator values. So I would encourage you to find first the work done. Okay, go ahead and solve, and the time given is 6.4 seconds. So once you solve this entire thing, you get 5.3 into 10 to the power of 4 watts. And you can't keep them in watts, because second part is asking you to convert the unit into horsepower. So the actual value in watts is this. Then we'll go ahead and convert 5.3 into 10 raised power 4 watts And we know that the conversion of watts to horsepower is 1 horsepower. In the previous problem, we just found out 1 horsepower is how much? 746 watts. So you want the horsepower to stay and you want the watts to go away. So 1 horsepower is equivalent to 746 watts. So the watts and watts will go away. You go ahead and solve 5.3 into 10 raised power 4 divided by 746 horsepower. Once you solve this with the help of calculator, your value should come out to be 71 horsepower. So this is the conversion part of the problem. So another interesting part of power and energy consumption is that whenever you get your bills at home for the electricity, it's basically not, you don't get billed for power, you get billed for energy. So you all agree that work and energy are interchangeable. So work is also energy, energy is also work, because you can only do work if you have energy. So that's why we can use them interchangeably. And power is measured in watts, you already know that. But electrical companies bill you for energy. So if power is energy over time, which is also work over time, you multiply both sides by T, you get power multiplied by time is energy. You are basically, the bill that you get at home, because you can't get a bill for a watt. Watt is a very small unit, so you use kilowatts of power, and they can't bill you for a second, because then it will be too many seconds over the month when you get the bill. So we use it for hours. So that is why the electrical energy bill that you get is kilowatt hour. You see on your electrical bills, you'll be billed for a kilowatt hour. So we'll work on one of the problems here on the kilowatt hour. So what is the cost of running a 0.200 kilowatt computer for 6 hours per day for 30 days if the cost of electricity is 0.120 per kilowatt hour? So how about you go get a head start and work on this one, because this is something that we all use every time. So cost is based on energy consumed. Thus, you will start working on it as energy is power multiplied by time, and then calculate the cost, because electrical energy is expressed in kilowatt hour, just as I discussed behind. That's the electrical energy unit. It's basically the unit of energy. It's not the unit of power. The unit of power is kilowatt. The unit of time is, the unit of time is hour. So power into time is energy. So basically this is the unit of electrical energy. So, okay, you found out that your computer consumes a power of 0.200 kilowatts for 6 hours. So if you are using your computer for 6 hours, let's see how much cost it will be. And per day for 30 days. So for the month, you're getting billed for 30 days. If the cost of electricity is 0.120 per kilowatt hour. So let's first find out how much electricity is being used. So electrical energy used is power multiplied by time. And that is 0.200 kilowatts multiplied by 6 hours. I don't want to keep it as 6 hours. we have to find out how, just to keep it in hours, but 6 hours per day. It's not only 6 hours for one day, it's per day. And that too, this is for 30 days. So multiplied it by 30 days. Okay, so for 30 days, how much energy is consumed by your computer? So if you solve this, you're using 36.0 kilowatt hour of energy in a month if your computer is consuming so much energy, 0.200 kilowatts per hour. So now let's find out how much it costs us. So cost is given by energy multiplied by the whatever is the price per kilowatt hour. So 36. So this is simple math that you would calculate, since you all must be paying your electrical bills, and it's a good way to know what you're getting billed for. 36 kilowatt hour was the energy that your computer consumed for 6 hours per day, 30 days, for 30 days. So this will give, now if I multiply it by the price, so that's the dollars, 0.120 per week, per kilowatt hour, not per week, per kilowatt hour. So the basic idea is, in the end, I should get the answer in dollars. So 0.120 is charged per kilowatt hour. If you multiply both of them, out of your electric bill, if you are using your laptop for 6 hours per day, for a month you're paying $4.32 per month. Cool. This way you can find out how much your appliances are costing. If your laptop alone or your computer alone is costing you $4.30 or whatever per month, how much will be your washer dryer? How much will be your dishwasher? How much will be your electrical gas stove if you have one? So that this can be a good project to do or to work on, to find out what is the kilowatt wattage of your different appliances at home, and how long do you use them, so you can find out why you are getting such a high bill. All right, so it's a good learning experience. Same way you can find out for your hair dryer, using it every day for 5 minutes. So how much, because hair dryer has a much higher wattage, so like 1200 watts of hair dryer per 10 minutes every day, or 5 minutes, depends on the use. So how much your hair dryer is costing you per month, you can even find that. I hope there's a problem in your Pearson in the homeworks on the website. I hope they have some examples which will treat you to some of the explanation on hair dryer problem as well, but I'm not sure if there is one. So lastly, what are the energy resources that we have, and how much is petroleum, how much of the energy sector in petroleum do we consume? 35.43%, and coal generates 28.15%, and dry natural gas 23.46%. Hydroelectricity, we have not tapped it completely, 6.27%. Nuclear electricity, not to that. This comes with a hazard though, but geothermal, solar, biomass, and wind, we are not using them optimally, and these may run out. So we have to start thinking, and since you are the next generation, it's your job to think how to minimize energy consumption, how to go more into renewable energy resources. So think alternate energy solutions, and I'm a big fan of this. We have solar panels on our roof, and for the past 5 years, and we really enjoy using air conditioner in the summer with paying very less. We sell our electrical energy to the grid back, so we basically get zero bill in summers. All right, so think about alternate energy resources. So basically, to summarize the chapter 6, we have our work done is force into distance into cosine theta. That is your chapter 6 part 1. We discussed this whole thing. We also talked about change in kinetic energy is the work done, which is work energy theorem. We also talked about potential energy associated with forces, potential energy being of two types. One is gravitational and one is elastic. We looked into springs and the problems, and we also have a lab based on Hooke's law, which has a lot of spring problems but not energy related though. The net work done on object equals the change in kinetic energy. That is the work energy theorem that you saw that we used even in the power problems. If only conservative forces are acting, mechanical energy is conserved. We talked about conservative and non-conservative forces, and non-conservative forces are those forces like friction, air resistance, heat due to the friction, and so on. We did not do any problems based on non-conservative forces. We treated them as zero in our problems. And then finally today we worked on power, and we also worked on energy, which is also power multiplied by time. So please do use office hours to ask questions, because the homework for this is due soon. And I also sent you the due dates for the assignments and everything, and last week in the announcement, which must have come to you. So pay special attention to the dates as we are winding down the semester. All right. And on Thursday, the next lecture, we'll start with chapter 7, and that's on momentum. So I hope you're doing your usual reading on the textbook. Do not ignore the readings first. I will go ahead and start chapter 7, which will be pre-recorded again, but use the office hours on Tuesdays and Thursdays to ask questions related to homework or any related to your lab. The next lab, which is due next Tuesday, is already uploaded, so your Tuesday lab for Hooke's law is there. It's an interesting simulation lab, not difficult but enjoyable one. All right, see you next time.